Thanks for coming, everyone, and I think we can get started. So my name is Michal Převrátil, and I'm the head of tooling at Ackee blockchain. We are smart contract auditors, mainly focusing on contracts built in Solidity for Ethereum, but we also do have a Solana team, the guys who love just Rust. And yeah, what's even more important is that we love building open source. So there are two leading products we are developing at Ackee blockchain. The first one is called Wake. It's a Python-based tool. It's open source, and so everyone can use it. And the second one is called Trident. It's a fuzzer for Solana, but well, we will talk mainly about Python-based tooling today. So we will mainly talk about Wake and also some other tooling. We also do onboard new people to the ecosystem, to the blockchain, through courses at the Czech Technical University in Prague, and also some Solana guys through the School of Solana and Solana programs. We have the pleasure to work with many exciting projects like Lido, Safe, or for example, Aave. And we've also received a couple of grants for the tooling, especially from Coinbase and Optimism. But let's start with the topic. So why we should use Python? First of all, Vitalik loves Python, and I think this is like it's enough for us to also like Python. But except for that, it's got very powerful syntax. So well, you can type just a few lines of code and still do very interesting, very powerful things. So Python is just cool. It's very easy to read. It's literally easy to read, but also pleasure to write. And also, it's got very strong debugging capabilities. There's interactive debugger, so you can basically, well, do anything in the debugger, not just list some info, but also execute code. So it's very powerful. And it's got also very strong testing capabilities because there's PyTest, which is like testing framework for Python. So Python is really good for testing, for debugging, and also for writing. Also, another reason is that Python is the most favorite language, well, after Solidity, obviously, in the Solidity developer survey from the last year that was published, I think it was 1 month ago. So Solidity developers also love Python. So Python is, well, very favorite language. And, well, let's move to the tooling itself. So I've got a couple of tools here. There's Slither, there's Ape, and so on. So I will start from the left. And we are trying to compare those tools in terms of their capabilities, their features. So the first one is Slither, as I said. It's obviously Python-based. It's open source. Everything here is actually open source. And all of those tools are also frameworks. And Slither especially is a framework for static analysis. So, well, it basically can detect some issues in your code base. There's also API for creating custom detectors, so you can even design your own. Well, it's still maintained. And it unfortunately doesn't have a language server, so, well, you cannot use it for, like, writing your code and see the syntax highlighting and go to a definition of a symbol and so on. But there's still an extension, so you can at least see the detections in VS Code. Then there's Ape, which is especially focusing on testing. And it's like, let's say, a follow-up of Brownie, which is unfortunately no longer maintained. There are still commits from time to time, but officially it's not maintained. So, well, Ape is like following Brownie in like the testing capabilities. And, well, then there's finally Brownie. Brownie actually supports fuzzing, even though it doesn't support it natively in a way there would be some, let's say, dedicated fuzzing engine, but there's an extension, a plugin for Brownie Hypothesis, and it basically allows to do some kind of fuzzing. Then we've got Hardhat for comparison here. So Hardhat is still obviously maintained. It can be used for testing, and it also has its own language server and also an extension for VS Code. Then there's Foundry, which is Rust-based, and it can be used for testing, for fuzzing. And I think that they are actually making some efforts to also become a static analysis tool. But as far as I know, I don't think there's any like detector ready to be used as of today. But I think there are some plans to also turn it into a static analysis tool, and maybe perhaps sometimes in the future also make a language server. And finally, there's Wake, which has all the capabilities. It's like a Swiss knife for Solidity development. And what I think what's actually cool about this slide is that it's outdated, because I'm very, very happy to say that after a couple of months of development, we have open sourced a new testing engine written in Rust. So Wake is no longer Python-based tool, but it's actually a hybrid tool with Python and Rust combined. And so, well, all the capabilities remain the same. Even the tests remain the same. So it's written in Python still. Well, the syntax is completely the same, but the testing core inside is in Rust. It's running within the same process, and so it's very fast. I will tell you about that later on. So let's start with the static analysis. And I've got an example here from Slitter. I believe a lot of you know Slitter. This is the output on the console. And well, Slitter has kind of, well, a lot of detectors implemented. On the other hand, some of the detectors are not well up to date, let's say, for the latest version of Solidity, because, well, those bugs can no longer be like written in the latest versions of Solidity, or some detections are actually covered by the Solidity compiler. And as I said, it also has an extension for VS Code, so basically all of those detections can also be shown right in VS Code. Then there's an example from Wake, and yes, so this is again a console output, and it also shows the code snippets for the relevant lines of code. And what I really like about Wake is that if you can see like the relative path, you can actually click on that in your terminal, and it will open up your VS Code or whatever you have, maybe cursor or anything, and it will show you this exact same line, so it's quite easy to just check your detection right from the command line. As I said, there's VS Code integration, which is basically the same for both Slitter and Wake, because, well, it's VS Code, it's VS Code's API, and so even how detections are shown in VS Code, it's basically the same. Basically, there's underlined line, and there's also some information about the detection itself. But let's move on from the static analysis to the extension. And now you may wonder why I will show you an extension when this talk should be about Python-based tooling. And the reason is that, well, basically, this is the only extension, as far as I know, that's Python-based. It's powered by Python. So actually, all of those features that I will be talking about are powered by Python. The extension for Wake, or powered by Wake, is called Solidity Wake. And if you want to check it out, there's a QR code. You can scan it, and it will open up in the marketplace with the extensions. It supports VS Code, cursor, and so on. And there are basically implemented basic features like go-to definitions, syntax highlighting, and, well, also some more interesting features, like, let's say you have a variable, and there's a label shown above the variable with the number of references. You can click on it, and it will show you all the references for the variable. Also, when you have a contract, you can basically see a label above the contract that's saying inheritance graph. When you click on that button, you can see the inheritance graph for a given contract, and even the nodes within the contract are actually links. So when you click on a node in that graph, you can see your code for the contract that's inherited from. This is new addition to our VS Code extension. It's called deploy and interact, and it's something like Remix. It's like Remix-like experience, but within VS Code, so you don't need to switch between those two tools. You can just choose VS Code, and, well, when you have a project, you can just compile. I don't think there's the compile button because we are on the second tab, but there's a compile button when you can compile all of your contracts within the workspace. Yeah, there it is. So there's compile. Once you have compiled all the contracts, you can see all of them. You can fill in some parameters for the deployment. And once you fill in, you can just deploy the contract. You have the transaction with all the information, call trace, events, and so on. And then when you have the contract deployed, you can see all the functions within the contract, and you can just send transactions or perform calls. And, well, yeah, it's a Remix-like experience, but within VS Code, and it's all powered by Python. The next animation is well, related to something called forking. So basically what you can do, you can pass a URL to any node, and you can fork the state, the chain, from that node into your local workspace. And so you can do basically integration testing because, well, you have all the contracts from some external chain, but you can also deploy your own contract to the same chain and do some interactions between them. And there's Etherscan, and the reason for that is you can copy any address from Etherscan or even Sourcify, and you can pass it into the UI, and it will fetch the ABI. And so, well, it's very easy because, well, you can just paste the address and see the interface, and you can interact even with some external contracts. So yeah, this is the deploy and interact UI within the extension. Let's move on to deployment and testing. And yeah, this is an example of how tests can be written in the Ape framework. And what's nice is the syntax is very easy to read, as I said, also to write because it's Python. And unfortunately, within the Ape framework, there's no support for typing. So if you try to hover over the function create pool, you will see something like that, which means it doesn't know what it is because, well, it's something dynamic created at the runtime, and so it won't help you to autocomplete and so on. Now, if we move on to Brownie, it's kind of the same, basically almost the same syntax, but, well, still there's no typing support. So if you move your cursor above the function, you see basically the same information. It doesn't know about the function itself. Now, if we check how it's done in Wake, there's a few more lines of code, basically because of import, and we also need to specify that we want to fork from some node. But additionally, if we check the create pool function, it knows about the function because there's typing support. So when you have a project, you can compile it. You can generate something called PyTypes, which is like typing stubs for your contract. And this way you can write any code in Python, but still aware of the functions, of the structures, events, and so on within your Solidity code base. So it helps you to write the code, and it even helps like the, let's say, AI agents or whatever you want to call it, basically the cursor and Copilot, let's say, because they now can see the Python stubs and they can help you write the code very efficiently. This is why we love Python, because it's got very strong debugging capabilities. So this is an example where we can run a test. And well, basically the debugging console is the same in Wake and also in Brownie. It's kind of the same. And it's got a lot of colors, and you can see, well, where your test failed. You can print any information. You can print call traces about the transactions you've performed, so you can check any transaction in the history. You can print call trace for such transaction. And you can even print local state within Python or interact with your contracts because the chain is still alive. So you can check any contract that's present on the chain, and you can even send new transactions, deploy new contracts, and so on. But Python is slow. Well, everyone claims that Python is slow. Well, sometimes it's slow. So what we did is we wanted to compare the performance of Python-based tooling also with Hardhat because it's also a dynamic language. And so we took Uniswap v3 repository. We took 271 tests that were originally written in Hardhat, in TypeScript. And we have re-implemented those tests into Brownie, Ape, and also Wake. We've also taken different, like, let's say, testing environments or development chains, and we have left, we let all the tests run with the specific configuration, and we've checked the execution times, how long it took to execute those 271 tests. And these are the results. It's always in seconds. And as you can see, Wake is pretty fast, even though it's running with Anvil. And even though it was still running all within Python. It wasn't measured with the new Rust execution core, and still it was very fast, especially with Anvil. So Python can be still quite fast if you use it properly. But, well, there wasn't Foundry, for example. So let's compare with Founder. But before we start comparing, let's speak very quickly about fuzzing, because I don't know how many of you have ever heard about fuzzing. Yeah, that's quite a few of hands. Thank you. So, well, fuzzing is basically about generating random sequences of transactions, also generating random parameters for such transactions. And since we are generating random data, we want to execute as many transactions as possible to make the fuzzing efficient and to have quite high chance that we will find some issues. This is a very simple example where we are doing, let's say, a unit test where we just transfer a few tokens, 1,000 tokens from Alice to Bob, and then we make assertion that the transfer was successful, that we've actually transferred all those tokens. And let's say that we want to rewrite that simple unit test into a fast test flow, into something that can be executed with fuzzing. So we need to randomize the parameters, and I think this is how I would do it, probably. So we choose a random account as a sender, also a random account as a recipient, and finally, we also generate a random value for the amount of tokens we want to send. And then we perform the transfer, and finally check if the transfer was successful or not. And how this is more powerful than this, I think it may be obvious, maybe it's not, but we may introduce collisions in between sender and the recipient. So we will see how the contract behaves when we have the same recipient and sender. And also, we may generate 0 here, so we can see how the contract behaves if we try to transfer 0 amount of tokens. So this is like the basic idea behind fuzzing. But let's move on to the second benchmark we've performed that was especially focused on fuzzing. So we took Daedalus benchmark, originally developed by Consensus, and there are 5 mazes. And you can imagine that it's like a grid 7 times 7. I will have an image there. And when we have those mazes, then we basically assigned 1 CPU core for each benchmark test, and we left that running for 20 minutes. And well, I will show you the image. So yeah, we started at the left bottom corner, and we can move in 4 different directions: up, down, left, right. And each time we are moving, we also need to specify 8 uint64 parameters. And depending if we specify those parameters, let's say correctly, or like, well, yeah, there are some preconditions. But if we specify those parameters correctly, then we may find an issue, a bug in that maze. And well, there are some bugs, as you can see, and this whole benchmark is only about trying to find as many bugs as possible within those 20 minutes. So this is also a signature of a function. This is one of those 4 functions, as we can move in 4 different directions. And yeah, so this is the idea behind the benchmark. This is an example of one of those bugs that can be found or maybe discovered by different tools for fuzzing. So the first condition is for the location within the grid. It's 7 times 7, so these are like the coordinates. And when we are moving to this cell within the grid, we need to specify all the parameters, that P0 to P7 parameters. And depending on the values, we may find or not find a bug, an issue. And some of those conditions are quite easy to satisfy, like P2 must not be equal to P6, but some of those are quite hard to satisfy, like, I don't know, I think there's P3 must be less than equal, less or equal to P0 multiplied by P3. That's basically, well, we can use 0, maybe 1. I guess that's maybe all. So some of those if conditions are not easy to satisfy. And finally, I think we can see the results. So these are the results for different fuzzers out there. As I said, there are 5 different mazes. And those numbers are the numbers of issues of bugs found within the maze 7 times 7 within those 20 minutes when assigned one CPU core. And you can see Echidna here. Probably many of you know what Echidna is. Also Foundry. Then there's Wake, but let's say the original Wake written in Python interacting with Anvil. And also the new Wake with the Rust testing core. So, well, based on these results, you can see that Wake was the worst when we were using just Python with Anvil. And now it has become the best just because of the performance improvement. Otherwise, the algorithm for generating random numbers is perfectly the same. It's completely the same, but the only difference is the execution speed, which you can also see here. We've measured how many transactions per second on average we've achieved. And so it was like, let's say, around 145 transactions per second with Wake plus Anvil, and almost 9,000 with the new Rust testing core. That's like 60x speed up. That's quite a lot. So, well, performance quite matters, especially in fuzzing. So if you ask me if Python has some future, like in Solidity ecosystem, I think it definitely has, and especially when it's combined with Rust. So there's like the best of both worlds, which is user experience interactions with Python. But when we need some good performance, we should use like Rust for the background job. So it's best combined together. And since I cannot speak for other tools, I can only speak for Wake. So if you wonder what's coming in the next version of Wake, as I said, there's the new Rust testing core engine, which is coming in Wake 5.0. It's based on REVM, on the Rust EVM engine. Also, there's coming support for Trezor, for Ledger, also for EIP 7702, which is like setting the code of externally owned accounts, and also, for example, support for ARM Linux, because, well, there are no official binaries from the Solidity team, so it's not possible to compile Solid code on this platform, but we will support it anyway. And I think that's pretty much all from my side. So if you want to well, check more about Wake, you can scan the QR code. It will lead to the landing page of Wake. Also, the name of the package for Python is called EatWake. And if you have any questions in the future, you can also join the Telegram group, so you can ask the questions there. But yeah, I think that's all from my side. And if you have any questions right here, right now, feel free to ask.
Security community, you know what to do. Do we have any questions in the audience? Here you go, sir.
What's actually like the difference between fuzzing in Python and against fuzzing in, for example, Solidity?
Yeah, so, well, these are two different approaches. And I think that Python is more powerful when it comes to debugging, because you have the interactive debugger, and you can stop at any point, and, well, you can execute new transactions, you can inspect anything. And I do believe that it's also simpler to write tests in Python because it's more user-friendly, it's very easy to write, and even there's like better support in IDEs, in VS Code and so on for Python than for Solidity. So, well, ultimately it's the decision for users. But, well, I think it's easier to write tests in Python.